Hello and welcome back, everybody. We're moving on to the first power rule for summation. Really not going to go through this much because it's so horrendous. We have these terms called the negative Bernoulli numbers that show up. Everything else should look familiar, right? So imagine if I got rid of these negative Bernoulli numbers, what you're looking at is the binomial coefficients, which are arising out of Pascal's triangle. And so if you remember Pascal's triangle, you should remember those binomial coefficients. You can also compute them as k factorial over j factorial, k minus j factorial. Either one is equivalent. And then we've got a sum of n to the j plus 1 divided by j plus 1. And so everything here should make sense from what you know so far. Kind of the only special term is going to be this b minus k minus j term. And it's got its own calculation. So here I have b minus sub m. So if you wanted to calculate the k minus j version of that, I'm going to replace this m with k minus j, but unfortunately I've already used a j there. So I would say just use the computation that I've provided below for these Bernoulli numbers and don't try to compute them with this lovely formula. You're going to be going crazy if you do that. So what have I actually done here is I've computed the first 11 of these. And so if you were ever asked to use this first power rule, just refer to them here with their subscripts. First one's 1, or the 0th one's 1. The first one's negative 1/2. Second one is 1/6. Third is 0. Fourth is negative 1 over 30. Fifth is 0. Sixth is 1 over 42. Seventh is 0. 8 is negative 1 over 30. 9 is 0. 10 is 5 over 66. 11 is 0. You'll notice all of the odd ones are 0 except for 1. So that kind of saves you a little bit of time. But these are the Bernoulli numbers. It's just kind of a lovely sequence to think about. I mean, you already experienced a lot of other good sequences, and this is just another one. So we have these Bernoulli numbers, and we just have to include them if we're going to take the indefinite sum of n to a specific power. Okay, so that is the proposition. It's really ugly. I'm going to go through a few examples. We're really going to do our best to not work with these because they are so horrendous. Well, let's go through a couple examples just to see that this actually works and how we may use the Bernoulli numbers. Let's do our first case of summing 1 n times. What do we think is going to happen if you add 1 to itself n times? We better get an n at the end of this, but let's actually go through the formula. 1 is equivalent to n to the 0 power, and my formula says I'm going to put that 0 in the top of the sum. I'm also going to put it in the top of the binomial term. I'm going to put it in the first entry in the Bernoulli terms, and then I'm actually going to perform this sum. Well, if my sum happens at j going from 0 up to 0, then I'm going to evaluate everything at j being 0, 0, 0, and 0. So I'm going to evaluate all of these with zeros, with the j's at zeros as well. Turns out the 0th Bernoulli number is 1, and the 0, 0 entry of Pascal's triangle is the top entry of Pascal's triangle, also a 1. N to the first power is going to be n divided by 0 plus 1, n divided by 1, and indeed we do recover n plus c. Cool, so it works in the case when n is 0. Let's try summing the first n numbers. And if we remember, there was an exercise on this. These are the triangle numbers. So let's see if we actually recover the formula for the triangle numbers out of this. If we add the first n integers to each other, this is going to be n to the first power. If we think about our formula from above, this formula, my power goes up here, so it'll be 1 up there, a 1 right here, and a 1 in the first entry of the Bernoulli number. And so here I have a 1 up top, a 1 in the binomial, and a 1 in the first entry of the Bernoulli numbers, and then I actually have to perform this sum. So when j is 0, I have 1 choose 0, the Bernoulli number 1 minus 0, and then my powers are going to be 0 plus 1 divided by 0 plus 1. Then I'm going to add, because this is a summation here, I'm going to add, moving j up to 1, 1 choose 1, the Bernoulli number of 1 minus 1, and then in the powers I'll have 1 plus 1 over 1 plus 1. If I evaluate everything that's happened there, I'm just going to refer back to my chart for the first Bernoulli number as well as the 0th Bernoulli number. The first Bernoulli number in the chart happens to be negative 1/2, and the 0th Bernoulli number happens to be 1. I also need Pascal's triangle for both of these coefficients. The first entry in the first row of Pascal is going to be 1. The second entry in the first row is going to be 1. And then my denominators are going to be 1 and 2 with their respective powers of 1 and 2. So if I formulate all of those and compute them out, I end up with n squared minus n over 2. Or if I simplify a little bit, n times n minus 1 over 2, which is in fact the formula for the triangle numbers, technically shifted by 1, and that's because of the way the finite difference is defined. So that's kind of cool that we do recover that formula for the triangle numbers. And we're going to stop at the sum of the n squared terms because, like I keep saying, this is horrendous and we really don't want to use this if we can avoid it. But I wanted to provide examples. In the case of n squared, let's recall where that 2 ends up. It ends up at the top of the summation. It ends up in the top of the binomial term, and it's the first term in the Bernoulli number. And then we're actually going to perform this summation starting at 0 and ending at 2. When j is 0, I'm going to have a 2 choose 0. Bernoulli 2 minus 0. J is 0, so I'm going to evaluate at the power 0 plus 1, and in the denominator 0 plus 1. Then on the summation, I'm going to add, moving j up to 1. 2 choose 1, Bernoulli number 2 minus 1, 1 in the power, 1 in the denominator, and then taking the summation one more time, moving from j equals 1 to j equals 2, I'll have 2 choose 2, Bernoulli number 2 minus 2, n to the power 2 plus 1 divided by 2 plus 1. Now if I actually evaluate all of these terms out, I will need to know Bernoulli number 2. If I go back to me having computed all of them for you, that happens to be 1/6. 2 choose 0 is going to be 1, my power is going to be 1, my denominator is going to be 1. 2 choose 1 is going to be 2. Bernoulli of 1 is going to be negative 1/2, and then power is going to be 2, and denominator is going to be 2. My last case, 2 choose 2 is going to be 1. Bernoulli number of 0 is going to be 1. N to the power 2 plus 1 is going to be n to the power 3, and denominator 2 plus 1 is going to be denominator 3. So that's what I have there. And if I choose to kind of factor this, add them all into the numerator and factor, I do have n times n minus 1 times 2n minus 1. These happen to be the pyramidal numbers, the square pyramidal numbers, and we're going to find out that I actually have an example on the square pyramidal numbers later during this textbook. Quite a bit later, not today. Anyway, try to avoid this if you can. It's horrendous. I've given you examples. If you happen to ever need to calculate these sums, it's definitely something a mathematician has to do every now and then. But we really don't want to think about it that way, right? We want to go to this second power rule for summations. The second power rule for summation, this is where we're dealing with the falling factorials, and this power rule just behaves so much more beautifully. So we're going to recall the falling factorials one more time, and falling factorial k is defined by n times n minus 1 times n minus 2 times n minus k minus 1. So it terminates at 1 less than k because we started at 0, so you still have k total terms here. But the summation of these just behaves so much better than the summation of regular powers. And we're going to use that, right? Well, how does this behave? This is exactly like our power rule for integrals. We're just going to add 1 to the power, and we're going to divide by the new power. And so I've got some examples of us using that here. In the case of 1, we can think of 1 as n to the 0 falling factorial, in which case we're just going to add 1 to the falling factorial, and we're going to divide by the new power, which is 0 plus 1. So that'll give us n falling factorial 1 divided by 1. If you compute n falling factorial 1, well, that's just equal to n times, well, there's nothing left. So it's just n plus c. So this was a much easier way of arriving at the answer that the sum of n terms of 1 is exactly n. We can do the same thing actually with n to the first power, because n to the first falling factorial is the same as n to the first power. And so what are we going to do is we're going to add 1 to the power of the falling factorial here, and we're going to divide by that new power. We're going to get n falling factorial 2 all over 2, and that arrives at exactly the same as we had before, this kind of shifted triangle numbers. We didn't have to go through the Bernoulli numbers to get there, because the falling factorial gave it to us. And we can actually compute this one step higher. We could compute the summation of n times n minus 1 over 2, also known as the summation of n squared over 2 minus n over 2. So either of those sums you can compute, and you're going to ask the question, oh, that numerator is n falling factorial 2. So you really are asking a question about the sum of n falling factorial 2 divided by 2. Well, how are we going to compute the summation? We're just going to add 1 to the power and divide by the new power. The 1/2 is coming along for the ride. That's going to give me 1/2 n to the falling factorial 3 over 3, or also known as n times n minus 1 times n minus 2 all over 6, right? Because this n minus 1, n minus 2 is the definition of the falling factorial 3. And so this gets just so much easier than what we used to have when it came to power rules, right? The falling factorial is really what we want to use. We also got our exponential rule. This comes directly from inverting the finite difference, right? If you recall the finite difference exponential rule, it gave you an a minus 1 times a to the nth power. We're just going to grab this minus 1, and we're going to divide both sides by it. So we have dividing by a minus 1 instead of multiplying by a minus 1. So this exponential rule is really nicely behaved. It still shows you that instead of e being the base that's invariant, 2 is the base that's invariant. This will give me 2 to the power n over 2 minus 1 plus c, but 2 minus 1 is just 1, so this is just 2 to the power n plus c. So that's our invariant base when it comes to summation. And we'll go through a nice little example of this. We can compute the sum of alternating negative 1s, right? How would this look? This would be negative 1 plus 1 minus 1 plus 1. And so this summation alternates between negative 1 and positive 1. And if we use our exponential rule on this summation, we get negative 1 to the n all over 2. Where did that come from? Well, the exponential rule says you keep your exponential term and you divide by, right? You divide by this minus 1. And so negative 1 minus 1 is negative 2, but I just pulled my negative out front. Now it's really weird to think about something like negative 1 plus 1 minus 1 plus 1 as some summation, giving me a 1/2 as the result. And the reason why the 1/2 actually makes sense is that we're computing an indefinite sum here, not a definite sum as would be there. If you actually convert this to a definite sum, you'll notice that you always subtract one of these from another when computing a definite sum. Okay, and if you subtract a 1/2 from itself, or if you add a 1/2 to itself, you do actually recover a whole number ratio, and it will give you the right answer here. So it feels kind of strange that the indefinite sum of integers in this case is not actually an integer. But if you compute the definite sum, it does send you back to be an integer. So it helps you that in action. Let's do the case of a definite sum starting at 0 and up to 10 of -1 to the nth power. So what would that be if I just added it out? That's -1 to the 0 plus -1, 1 plus -1 squared plus -1 cubed plus dot 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 plus -1 to the 10th. Now what should that be? Well, if you think about it, each of the terms are going to cancel because that's 1 minus 1, that's 1 minus 1, and so on, except this term is going to be left alone. You expect this to be 1 when you finish. But let's actually see this happen. If you use your definite sum formula, right, the definite sum formula says take the top bound, add 1 to it, and that goes into the indefinite sum, and then you take your bottom bound and you subtract it for the indefinite sum, right? So this is the fundamental theorem of calculus, in this case discrete calculus. Well, if you evaluate at capital A sub 11, that's me putting an 11 in here, that's going to give me a negative 1/2, also known as positive 1/2. That's what I've got here, negative 1/2 or positive 1/2. Then you evaluate at 0. If I evaluate this at 0, that's -1 to the 0 over 2, also known as -1/2. So I'm going to have a positive 1/2 minus a negative 1/2, or positive 1/2 plus 1/2. I will recover 1 like I expect. I can just do the indefinite sum of 5 to the n as well. That says, hey, my exponential stays the same, this 5 to the n, but I'm going to divide by the base minus 1, so that's going to give me 5 to the n over 4. I could even do something like this complex exponential. We remember this from maybe the polar complex numbers or Euler's identity. But now we're going to take a sum of a lot of these, and the way the sum works, as an indefinite sum at least, we keep, by recognizing that this is really e to the I pi x to the nth power, we keep the exponential the same, so there it is, and then we're going to take the base, which is just the inside of it, e to the I pi x, and we're going to subtract 1 from it in the denominator. I can then distribute that n back into my exponential, and I end up with this as a result. Now this would actually be useful for a course with Fourier series. If you've never heard of that, don't worry about it for now, but if Fourier series is something that interests you, I would look it up, and that's really what you're computing here, is kind of the result of a Fourier series. Logarithm rule says I'm going to take the indefinite sum of a log of base a. Actually, a little typo, you can have base a on the right hand side as well, and it's going to be the log of the factorial of a shift by 1 on n. And this is just straight out of, I kind of covered that earlier, is that you can always define an indefinite sum as a definite sum with a variable upper bound. And if we do that with the variable upper bound n minus 1, then its definition is to add a bunch of logarithms together. Well, what can we actually do here? We can use the log rule for addition, which tells us we can multiply terms on the inside of a log instead of add terms outside of a log. And what are we doing here? Well, we're multiplying consecutive integers up to n minus 1. That's exactly the definition of the factorial. And so the log rule says if I take a sum of a log, I actually have the log of the factorial, but the index has been shifted down by 1. Let's look at a couple examples of these. Pretty straightforward. We do the natural log, take the sum of the natural log of n. We're just going to replace n with n minus 1 factorial. Of course, you preserve base e here. Similarly with log base 10, we're just going to have log base 10 of n minus 1 factorial. We preserve base 10 in that case. One last rule, just like we had integration by parts, there is a summation by parts, and this is going to do the same job of integration by parts in the sense that you'll notice on the left-hand side we've got some sequence b sub n here, and on the right-hand side it's been replaced by its derivative. So we're going to be able to replace a multiplied sequence term with its derivative. And this is good if the derivative is simpler than the sequence itself. right? In the case of integration by parts, if I had something like x e to the minus x dx, I would want to take the derivative of this x, because what is the derivative of x? Well, it's 1, and so that makes my life a lot easier. In the case of a summation, you can imagine if I have the sum of n e to the n, you would want to take the difference, the finite difference of this n, because the finite difference of n is 1, and so that also gets simpler. So you have the same sort of idea where you can reduce the power of monomial terms to compute indefinite summations. But the price you pay, just like with integration, is if you're taking a derivative of one term, you have to take an antiderivative of another term. Recall, capital AN is going to be the indefinite sum of lowercase an. And so you pay the price by taking the derivative on b, you have to take this antiderivative on a, you get this capital A, and we also have to pay the price of a shift by +1 in the inside sum A, capital A. So the inside sum, capital A, is going to be shifted by +1. But otherwise, everything looks the same. The proof is exactly the same as the proof of integration by parts for integrals. We are going to go through just 2 examples of combining a few of these sum rules now that we actually have summation by parts. So what you'll see here is I have a multiplication of n times n minus 2 times 2 to the nth power. We're going to recognize that if I took a finite difference of n times n minus 2, that term's going to get easier. And in fact, taking the indefinite sum of 2 to the n is quite easy because that is itself, right? Recall that 2 is the invariant base for both finite differences and summations. And so we're going to get an easier term when we take a difference of n times n minus 2. We're going to be able to take the antidifference of 2 to the nth power. And so that's going to tell us to use summation by parts, particularly with capital A being up there, and then b, lowercase b, being this n times n minus 2. Okay, so if we do that, we're going to name lowercase a sub n as 2 to the n, and then b sub n as either n times n minus 2, or if I expand that, n squared minus 2n. And then I'm going to compute the indefinite summation of 2 to the n, which is 2 to the n. I'm going to compute the finite difference of b sub n, which would be the finite difference of n squared minus 2n. And if you remember our finite difference rules, well, the finite difference of n squared, that's going to be n plus 1 squared minus n squared. This will simplify to n squared plus 2n plus 1 minus n squared. Well, the n squareds cancel, and we have 2n plus 1. And then the finite difference of negative 2n will be negative 2n plus 1 minus negative 2n. That's going to be negative 2n minus 2 plus 2n. The 2n's are going to cancel, I'll have a minus 2. So what is 2n plus 1 minus 2? That's just going to be 2n minus 1. And so that'll be the finite difference of b, and we're just going to plug capital AN and delta BN and BN and capital AN into our summation by parts formula. That's going to give me, well, here's capital AN, here's BN minus the indefinite sum, capital AN plus 1, right? So this is n plus 1, so I need to add n plus 1 there. So AN plus 1 times delta BN. And now I've got really one term that's been computed for me, and then another term that is yet again another indefinite summation, but I can simplify that indefinite sum a little bit, right? Because I've got a minus sign here. So I'm going to go ahead and distribute 2 to the n plus 1 to both terms there, and then I'm going to use linearity of the sum to distribute even the sum to both terms. That's going to give me, on the left-hand term, the sum of 2 to the n plus 1 times 2n, and on the right-hand term, I've got a minus and another minus, so I'll have a plus, the indefinite sum of, well, 2 to the n plus 1. That's the term that came through. Okay, I can simplify each of those terms a little bit more, right? Because I've got really this plus 1 is going to be one copy of 2. That 2 is going to be another copy of 2. So it'll be a 4 hanging out on the first summation. And then this plus 1 will be one copy of 2. So I've got a 2 on the other summation. We're going to have really our first term, and then we'll be subtracting 4 times really this summation that we maybe don't know how to compute yet, plus 2 times this summation, which we do know how to compute because that's just another exponential rule. The sum of the exponential is itself. And so that one's easy to compute. We just have to compute this summation of 2 to the n times n. We're going to use one more round of summation by parts on that. In this case, we're going to say, oh, that gets easier if I take a finite difference. So I'm going to call that b. And I certainly know how to take an indefinite sum of 2 to the n, so I'm going to call that a. The indefinite sum of a will still be 2 to the n. The finite difference of b is the finite difference of n. That's going to be 1. And so when I do this summation by parts, well, I'm just going to compute this on, let's see, this is capital A, this is b minus capital A, n plus 1 times delta b. And so I'm going to put those 4 terms in, and what I end up with is n times 2 to the n minus 2 times the summation of 2 to the n, and the summation of 2 to the n is just itself. So if I simplify that a little bit, I end up with n minus 2 times 2 to the n. So that was just this last term that I computed. Everything else I know how to compute. If I combine all those terms together, then what do I end up with? Well, I end up with the first term minus 4 times the term I just computed, which was n minus 2 times 2 to the n, plus 2 times this indefinite sum, which we know is just 2 to the n. And so I end up with n times n minus 2, 2 to the n, minus 4, n minus 2, 2 to the n, plus 2 times 2 to the n. If I kind of factor everything except for 2 to the n out front, I have n squared minus 2n minus 4n plus 8 plus 2, also known as n squared minus 6n plus 10 times 2 to the n. Now, why is this important? Well, you could actually compute quite quickly something like n starting at 0 and ending at 10, n times n minus 2 times 2 to the n, rather than having to write these out as 0 times 0 minus 2 times 2 to the 0 plus 1 times 1 minus 2 times 2 to the 1 plus 2 times 2 minus 2 times 2 to the 2 plus dot 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 all the way out to 10 times 10 minus 2 times 2 to the 10th. You could compute it quite quickly as A11, capital A11 minus capital A0, where capital A is given above. If we did that in this case, you end up with a very quick value of 133,110. Save yourself a lot of time by being able to use these summation rules. And then we're going to move on to one last example before everybody gets to try these in their assignments. This example is going to be to compute the indefinite sum of n times log n plus log n factorial. And your alarm bells should be jumping off, telling yourself, remember that the indefinite sum of the natural log was the natural log of the factorial, but very slightly different, where the factorial has been shifted by 1. So this should really be jumping out as kind of this capital A n plus 1 term from summation by parts. And let's see if that's actually what's going on with that log of n factorial. So what we're going to do here is we're actually going to compute the indefinite sum of these two terms separately, and really we're just going to compute the indefinite sum of the left-hand term first, and that term is n times log n. We're going to be asking ourselves, should we use a summation by parts on this? Well, we kind of have to. We don't have any other rules that are going to work so great for us. And we would like to choose one of the terms to get, quote-unquote, easier with a finite difference. And of course, n does that because the finite difference of n is just 1. And we are able to compute kind of the anti-finite difference of log n. It's what I was saying from before. It really is log of n factorial. So since we're able to compute that antiderivative and it's easier to have a finite difference of n, which is just 1, we're going to choose n to be our b sub n and log to be our a sub n when we use our summation by parts formula. So that's what we've got down here, a and b, and we go ahead and calculate capital A. We know from our log formula or our log rule that will just be log of n minus 1 factorial, and maybe everybody's favorite finite difference to compute would be the difference of n itself, which is just 1. Okay, so we plug those in. Let's remember our formula really quick. I mean, that's having it all plugged in. But let's recall our summation by parts formula. It says the sum of an times bn is going to be, well, it's going to be capital AN times Bn minus the sum of AN times delta Bn. That would be integration by parts as it is, but summation, we have a very slight modification that we have to have a subscript n plus 1 on the integrated term or the summed term. And summation by parts. Okay, so what does that mean when we actually write it down here? Well, that means that the sum of n times log n, we're going to grab bn here, and that's going to be n. We're going to grab capital AN, which we just computed as log n minus 1 factorial. We're going to multiply those together. Then we have a minus, we've got the summation, and we've got the summation. We're looking at now capital A n plus 1. So I'm going to substitute n for n plus 1 here. What would that give me? Well, it would give me n plus 1 minus 1 factorial, also known as n factorial. So I'm going to substitute in a log of n factorial. I'm going to multiply by delta b, which we know is just 1. And so this summation by parts term will just be n times log n minus 1 factorial minus what's remaining here. So I'll have my minus log n factorial term. And now that's really jumping out from the beginning, right? Because at the beginning I had a plus log n factorial term over here, right? There was really a sum plus log n factorial, and my summation by parts has just given me a minus sum of log n factorial. So it turns out those two terms are going to cancel, right? If I write out my full summation here of both terms, then the left-hand term is going to give me a minus integral or summation log n factorial, and what's remaining is going to be the plus log factorial. Those two terms exactly cancel, and overall I'm just left with n log n minus 1 factorial. So that was a very quaint example showing that sometimes it's definitely to your advantage to interpret each term in indefinite sum like this individually. Compute your rules on each of them individually first, and then try to see if you can simplify at one step, or if something cancels. In this case, everything did cancel pretty nicely, so we're able to compute that nice and closed form. Anyway, that's all I've got for you today. It's a little bit more practice, right? We're getting all these new rules that make our lives a little bit harder compared to what we've been used to. I mean, now we've got to juggle both integrals and derivatives, as well as these discrete integrals and derivatives being sums and finite differences in our heads. But it's all good practice, right? Because what I want you to think about is we've got our table of rules. Every time you approach one of these, send yourself to the table. See, it's really a puzzle. You're trying to figure out what combination of these rules is going to solve the problem for you. And of course, I'm never going to present you with a problem that's unsolvable. So trust that there will be a solution. Hang in there. Give yourself some grace to be wrong when you're trying to figure these out, but I believe in you. Anyway, that's all I've got for today. See you in the next one. It's my favorite chapter of the book. It's the reason I wrote the book. It's called Dynamics. See you then. Bye.